Hey everyone, and welcome back to The Explainer. So today we're looking at a truly fascinating leap forward in artificial intelligence. You know, when we normally think about AI agents working together to solve a complex problem, we usually picture them kind of chatting with each other, right? Just passing text back and forth, like coworkers in a Slack channel. But what if they didn't have to talk at all? What if, instead of clunky, slow text chats, they could just instantly share their thoughts? Well, today we are unpacking a groundbreaking new paper that introduces exactly that. It's essentially a mind meld for AI, moving us from slow, word-by-word collaboration into a seamless, instant, almost telepathic future. All right, here is our roadmap for today. We're going to start by identifying the AI collaboration bottleneck, then step into the latent space, see exactly how we link the recursive loop, look at 4 patterns of collaboration, and finally, dive into the real-world metrics that make this whole thing faster, smarter, and cheaper. It's a clear roadmap from the current limits of multi-agent systems straight to some massive real-world performance gains.
Okay, let's dive right into this. Section 1. The AI collaboration bottleneck.
So before we look at the solution, we really have to understand the roadblock. How do AI models talk to each other right now? Well, in modern multi-agent systems, agents are still forced to communicate via standard text. They actually sit there and wait for full responses to be generated token by token before acting. Imagine forcing a team of top-tier, brilliant experts to communicate exclusively by writing slow, formal letters back and forth. It's a massive latency bottleneck, and it drastically slows down inference time while driving your compute costs right through the roof.
And that brings us to the core breakthrough of this research. Look at the contrast here. With a standard multi-agent system, or MAS, interactions are entirely text-based. It's slow, it suffers from incredibly high latency, and it is ridiculously token-heavy, which just drains expensive compute power. But then you have RecursiveMAS. This is the new framework proposed in the paper, and it's fast, it's seamless, and it operates in a unified latent space. It literally allows the models to mind meld. They don't type out every single word anymore, they communicate using their hidden underlying mathematical representations.
Which leads us nicely into Section 2, Enter the Latent Space.
We are taking collaboration entirely away from human text. The paper officially defines this concept as recursive multi-agent evolution. Now, instead of getting bogged down in dense academic jargon, let's just break it down simply. Instead of passing words, these agents are continuously passing their inner thoughts. Each agent actively adjusts its internal understanding, what we call its latent state, through repeated, iterative loops with the other agents, bouncing ideas back and forth until the entire system completely aligns on the right answer.
Moving right along, Section 3, Linking the Recursive Loop.
Now, what's really interesting about this slide is how the actual mechanics happen behind the scenes. You might be thinking, wow, do we have to retrain massive models from scratch to do this? We absolutely don't. The researchers designed something incredibly lightweight called a RecursiveLink. It's basically a 2-layer residual projection module, and it handles 2 distinct jobs. First, there's the inner link, which helps an individual agent consolidate its own ongoing latent thoughts between its input and output spaces. Then we have the outer link. This is the bridge. It connects the hidden representations across totally different heterogeneous agents. So even if you're hooking up a tiny coding model to a massive math model, the outer link translates that latent thought so the next agent can understand it perfectly. It's like a universal translator for AI brains.
So, how do they teach the agents to use these links? The researchers use a progressive co-optimization training paradigm. It's basically a 2-step inner-outer loop. Step 1 is the inner loop, where the agents just parallelly warm up independently, training their inner links to align with their own latent thoughts. Then, in Step 2, the system truly connects. The outer loop kicks in, and the whole system optimizes together. Gradients, which are basically the mathematical signals that tell an AI how to improve, are shared and backpropagated across the entire system over multiple recursion rounds.
And this brilliantly illustrates the final setup in motion. All the agents are literally chained together in a unified, continuous loop. They're passing these rich, dense, latent states back and forth round after round. But here's the absolute most important part of this architecture. Only the final agent in the final round of the loop actually produces a textual output for the user to read. By keeping everything else completely in the latent space, RecursiveMAS completely avoids the gradient vanishing problem that totally plagues standard text-based setups. The learning signal just stays incredibly strong across the whole team.
Okay, let's jump to Section 4, 4 patterns of collaboration. Because this isn't just some neat theoretical trick, it is incredibly versatile across multiple different model families. They actually tested this across 4 totally distinct styles. You've got sequential chains of planners and solvers. You've got mixtures of parallel domain experts, distillation, where a slow expert teaches a fast learner, and finally, deliberative loops between reflectors and tool callers. And they evaluated all of this across 9 distinct benchmarks spanning math, science, search, and coding.
The beauty here is that RecursiveMAS is entirely structure agnostic. It really doesn't care how you arrange your AI models. It adapts to however developers want to organize their specialized AI team. Just like puzzle pieces fitting perfectly together, it seamlessly locks those heterogeneous agents into a unified solution. And let me tell you, this saves engineers an immense amount of time because you don't have to rebuild your entire system from the ground up just because you want to change how your agents collaborate.
Now, let's look at the actual data. Check out this mixture-style collaboration performance chart. Take a look at those tall, dark blue bars on the right side of each cluster. That is RecursiveMAS. Whether we're looking at the AMIE 2026 math benchmark or the MedQA medical benchmark, RecursiveMAS isn't just participating here. It is decisively outperforming the individual science, math, and code specialists working in isolation. And it easily beats out standard multi-agent setups too.
Which brings us to the grand finale, Section 5. Faster, smarter, and cheaper. Let's look at the real metrics that prove this architecture totally crushes the benchmarks.
First punch, accuracy. RecursiveMAS delivers a consistent average improvement of 8.3% over advanced single and multi-agent baselines. Because they're communicating a much richer, continuous stream of information, rather than being artificially constrained by clunky human vocabulary, they simply make smarter, more accurate decisions.
Second punch, speed. Since these agents aren't waiting around to generate and read text token by token, we see up to a 2.4 times end-to-end inference speedup. Think about that. You get a significantly smarter answer, and you get it more than twice as fast.
So the crucial point is really this final metric, a massive token usage reduction of up to 75.6%. In the world of AI, tokens are literally money. If you can cut your token generation by over 75%, you are drastically slashing compute costs. It's not just faster and smarter. This makes advanced AI collaboration significantly cheaper to run at scale. It's a real game changer.
And if you want visual proof of how this system literally scales its own intelligence, take a look at this heat map for the Math 500 benchmark. On the axes, you have the recursion rounds, which is basically how many loops of thought the system is allowed to take. As we move up and to the right into deeper recursion rounds, the accuracy climbs from the mid-70s all the way up to 78.4. By simply allowing the latent loop to cycle a few more times, the system scales its own cognitive capability on the fly.
To quote the researchers directly, we co-evolve and scale the entire system as an integrated whole. The big takeaway for you today is that the future of multi-agent AI isn't just about throwing a bunch of standalone models into a chat room together and hoping they solve a problem. No, it's about linking them into a unified, breathing, latent ecosystem where the whole becomes far greater, far faster, and far cheaper than the sum of its parts.
Which leaves us with a fascinating, almost slightly eerie thought to wrap up on. Human language is actually incredibly limiting. It compresses our vast, complex thoughts into narrow little words. So, if AI agents no longer need human language to think together and can just continuously loop their raw, unfiltered mathematical concepts, what kinds of solutions, what kinds of entirely new concepts will they discover in the pure silence of the latent space? It's a strange, highly efficient future, and it's arriving very, very fast. Thanks so much for joining me on this explainer, and I will see you on the next one.